Good morning. I hope you don't mind having a video lecture for today and Wednesday's class. This is lecture number 3. And please, if you have not signed at least one of the attendance sheets from last week, Monday or Wednesday last week, and I'm talking about the lecture, not necessarily, not the lab, but the lecture specifically. If you have not signed one of the attendance sheets, please go see Mr. Fred Bowles in room CC 1190 and ask him to sign one of the 1111 lecture attendance sheets for Jim Gwynn's lecture class. It's very, very important that you make sure that you sign at least one of those so that you do not get no-showed during the no-show period. Okay, today we are going to start, alright, so don't forget Fred Bowles, CC 1190. We are going to start section 2, which is entitled Kinematics in one dimension. First of all, kinematics this is the study of motion. In other words, the study of how objects move. Not why they move or why they have the particular type of motion that they do, but just a look at their motion. What different kinds of motions can objects have? We will start out with one dimension for several reasons. First of all, it's a very good approximation for many different kinds of motions. Anything that can be described basically with one variable to describe where an object is as a function of time, is basically one-dimensional motion. If you're driving down a highway, basically all you're interested in is how far you've gone, not whether you're in the left lane, the right lane, the center lane, or something like that. All you really care about is one dimension of your motion. So that's essentially one-dimensional motion. So many types of motions are at least approximately one-dimensional. And also, once we get a good understanding of one-dimensional motion, it will lead very, very easily and directly into two-dimensional motion, three-dimensional motion. So it's a good start for us to get into more complicated behaviors later on. Okay, so in order to start with the study of motion, our first question that we'd like to ask is, where is the thing, whatever the thing is that we're talking about. Typically, we're talking about the motion of an object, and so one object at a time typically. Where is it? Where is this object? Well, in order to describe where something is, what we're going to use is a coordinate system. And for one-dimensional motion, we need a one-dimensional coordinate system. Very simply, imagine something like a meter stick. So here I have a 2-meter stick, and we're going to choose a couple important points. First, we're going to choose one point on the meter stick. We're going to call this the origin, and we'll label this 0. Any positions to the right, and I mean to your right, typically to the right of the origin, we'll call these positive positions. And any position will have a value that corresponds to the distance from the origin. So let's say this position here, this would be plus 40 centimeters, because it is 40 centimeters to the right of the origin. Any point to the left of the origin, we'll call these negative positions. So, for example, say this position would be negative 40 centimeters, because it is 40 centimeters to the left of the origin. So, let's imagine we've got some object. So, here's a little man. And we want to identify, say, the position of where the little person is. So, let's imagine he's sitting over here. We can identify the position that he has, his position vector, and we will describe positions with a vector because not only is the distance important, but the direction, left, right, or left, the direction is important. So we'll define or describe the position that this little man has with a position vector. Okay. the symbol that we'll use for position vector will be r vector, or the r vector. So this is what we will call the position vector. And we'll use that to describe the location of our object, our little man or whatever. So let's draw this out. So here's our coordinate system, and we'll assume that it goes as far as we want, left to right. We'll choose some point as our origin. Let's imagine our little man is, say, over here. The position vector, remember a vector has a magnitude or length and a direction, will define the position vector as a vector that goes from the origin to the point where the object is. And so that will be our vector r. So notice it has a particular length and a particular direction, and the direction is telling us the direction of the object relative to the origin. Now let's imagine that perhaps our little man is going for a walk. So perhaps he's walking over here. Maybe he stops, turns around, walks back here. Maybe he even goes to the left of the origin, stops, comes back, whatever. So let's imagine that our little object is moving around. So in that case, our position vector, r, could be a function of time. It could vary for different times. So let's make a little chart. Let's say we have time and position. One way we could describe the motion of our object is to say at some time, let's say we'll call it t1. t1 might be 12 o'clock, or it could be 5:30, it could be 6 seconds, or whatever. Some time t1, let's say that our object is at a position r1. At some later time, let's say t2, our object is at some other position r2. Later time t3, our object is at some other position r3, and as long as the object is moving, r1, r2, r3 will all be different vectors. They could be the same vector, they could be different vectors. So this is one way that we can use to describe the motion, to say at what time the object is at a particular position, and that's one way that we can describe where the object is. Another way might be to actually give an equation for the position, an equation that would give the position at different times. For example, we might say that the r vector as a function of time is equal to, let's say, something like 2 centimeters per second times t, and then I'm going to use that unit vector we mentioned before, x hat. This tells us that we are talking about the x coordinate, or the only coordinate we have in this case, the x coordinate system, and so r is equal to 2 centimeters per second times t x hat. So what do we get in this case? Well, let's imagine that our initial time, t1, is, let's say, 0 seconds. So 0 seconds will be, say, our initial time, kind of analogous to our 0 position for the coordinate system. This would be the time when we want to say we start our clock. We start the stopwatch at 0 seconds. Put in 0 seconds here, what do we get? 2 times 0 is 0, so what's the position? It's 0. Or you could say 0 times x hat. I'll just say 0. Let's say at a later time, let's say 1 second later. So when t is 1 second, what do we get? We put in 1 second here. 1 times 2 is 2. Seconds in the numerator, seconds in the denominator cancel. What do we get? R is equal to 2 centimeters x hat. What do we get, let's say, at 2 seconds? Put in 2 here. 2 times 2 is 4. Seconds cancel. We get 4 centimeters x hat. At 3 seconds, we get 6 centimeters x hat, etc., etc., etc. What does this motion look like? Well, our little man is starting off here at 0. 1 second later, he's over here at 2 centimeters. Over here, over here, over here, over here. Looks like we've got some kind of uniform motion where the little man is walking off to the right, moving 2 centimeters further along every second. So that would be another way that we could describe the motion. If we had some equation giving the position vector as a function of time, and we could put in whatever value of time we want. Now, another very important quantity that we will be using, in addition to position, is the change in the position, what we will call the displacement. The change in position is also going to be a vector, so this will be the displacement vector. And we will write this as delta r vector. Delta is going to be a very common symbol that we will use, which will mean the change in something, change in anything. And in this case, it's the change in the position. Now, don't think that this is some kind of multiplication here. Delta r, or delta times r. It's not. This is a different symbol, a new symbol. We might just as well call this d vector or something like that. Delta r is a single quantity. Don't think of that as any kind of multiplication or something. Delta r is going to be the change in the position. So displacement vector, this means the change in position. The change in the position vector. And we will define this using two different vectors. We need to know where does the object start and where does it end up. We might describe these with r final and r initial, say r sub f for r final, r sub initial, r sub I for r initial. And in that case it would be rf minus ri. So the final vector minus the initial vector. Now typically I'm not going to use these subscripts. Sometimes I will, sometimes not. Typically for the final vector I will just use r without a subscript. So r with no subscript means the final position. And then to indicate the initial position, I will write r sub o. So r final vector, final position vector, r sub o, initial position vector. All right, now remember what vector subtraction means. We talked about this last time. So let's just think about this. Remember, if we have two vectors, say a minus b, if we take a minus b, that's like saying a plus the negative of b. So if we've got two vectors, let's say here's a and here is b, we find the negative of b, and the negative of b is a vector that points in the opposite direction to b with the same magnitude. And then to add these, we take negative b and we put it on the head of a, so there is negative b. A plus negative b then gives us a vector that goes from the tail of the first to the head of the second. So from here to here, that would be a minus b. And it doesn't matter if we take a minus b or negative b plus a. We could take negative b and add a to it. And what do we end up with? Here's a, so we add a and we end up with the same vector a minus b. So it doesn't matter the order that you combine them, a plus negative b or negative b plus a, you get the same thing. But a minus b is not the same as b minus a. That would be the negative of each other. All right, so let's look at this. What do we have? R minus r naught. So let's imagine we've got our coordinate system here. Our little man starts out, say, here. Here is r naught. And let's say ends up here. So here is r. Now what's r minus r naught going to be? Well, what's negative r naught? Negative r naught is this vector here. Negative r naught. So what is negative r naught plus r? Well, we're going from here to here. Put the tail of r onto the head of negative r naught, over to here. So what is negative r naught plus r? In other words, r minus r naught. It's a vector that goes from this point to that point, and that is r minus r naught. In other words, that is delta r. So delta r is a vector that goes from the initial position to the final position. Delta r basically tells us the change in position. A vector that goes from where we start to where we end up. That's delta r, the change in the position. Notice that delta r gives the magnitude of the displacement. In other words, what's the total change, what's the total distance from the initial to the final place, and it also gives us the direction. In this case, the motion was to the right. Delta r is pointing to the right. Now, let's think about this. What do these values tell us? If r is larger than r naught, now I'm kind of using this very loosely. I know these are vectors. Let's just imagine we've got r is some large number times x hat, r naught is a small number times x hat, and I'll stick some numbers in just a second. But let's say that r is greater than r naught, okay, we don't usually think of vectors as being greater than the other or anything. What I really mean is the magnitude, but I'm also thinking about the direction, just positives and negatives. Then what do we get? We get delta r is going to be some positive number, loosely speaking. In other words, it's going to be a positive number times x hat. In other words, delta r will point to the right. So if r is further to the right than r naught, delta r will be a vector that points to the right. And what do we have? We've got motion to the right. What if r is less than r naught, so to speak? Well, what do we get in that case? Delta r is going to be less than 0. In other words, we're starting out somewhere further to the right, ending up somewhere to the left. What do we have? We're going to end up with a negative displacement, some negative number times x hat. We've got motion to the left. What if r is equal to r naught? What do we get in that case? R minus r naught will be 0. Delta r will be 0. What do we get? No motion. Now, let's be a little bit careful here. I'm going to say no net motion. Does that mean there was no motion at all? No, it doesn't. Imagine that our little man started out here initially, walked over here, and then came back to where he started. The initial position and the final position are the same. Delta r will be 0. But that doesn't mean there was no motion. It just means there was no net motion. The position where he ended up was the same as where he started, so there was no net motion, even though he moved to the left and moved to the right, or moved to the right and to the left. During that time interval, the net motion ended up to be 0. Okay, so let's stick some numbers in here. So just like we were saying, we might have something like r naught is, let's say, 3 meters x hat. R is 7 meters x hat. And what do we get? Delta r will be 7 meters x hat minus 3 meters x hat, 4 meters x hat. What do we have? We have the object starting out here at 3, ending up at 7. We get a positive displacement, motion to the right. Let's try reversing this. What if we what if we start out at 7 and end up at 3? Delta r is what? 3 minus 7, negative 4. So in that case, we're starting out at 7, moving to 3, we end up with a negative displacement. In other words, motion to the left. What if we start out at 7 and end up at 7? Our displacement is 0. We could write this as 0 meters x hat or just 0. What do we end up with? We end up with whatever goes on in between the beginning and the end. We start at one point, end up at the same point, 0 net motion. Now don't confuse displacement with distance traveled. The person could actually move a distance, but the net displacement during that time interval would be 0. Okay, now that's great. That's displacement. Now, the one thing displacement does not tell us is how fast did this motion take place. What's the time for r naught? What's the time for r? Perhaps r naught occurred at 0 seconds while r was 1 second later. Or maybe r was 1 day later. Or a year later. Displacement does not tell us how rapidly this motion took place. To do that, we need another quantity that we will define as velocity.